seconds.
3 books, and things like that. So the online courses that are part of the regular campus, so they are called I courses. This is one course. So I used to teach, as everybody, regular courses in this lecture room, until my department asked me to teach this course, an I course. In my regular old courses, I have a review session before every test. So when I did an I course for the first time, I scheduled a review session. So the next day I got an angry note from a student saying that that was unfair because he had signed up for the course just because he couldn't come to campus, and I was giving extra attention to students who couldn't make it to campus. So I decided that maybe this is not politically correct to write courses. So I did do it in the session except for the final exam. Now, what I did, I have these online office hours, and they used to be really well attended. We did a lot of review there. This semester, something happened, and nobody showed up at the online reviews. They said, well, I'm missing contact with students, I don't know what they're thinking. So I came up with Piazza. Piazza has been a failure so far. Didn't get anybody to get involved. So I said, well, I'm just going to do something. I'm going to do a live session, see if I can get you engaged. But I think it is important. There is no way you can learn physics from reading a book. It's impossible. So you really need to discuss physics with somebody who you trust. Okay? And I may not be the person you can trust the most, but I'm being paid for being that person. So you probably, and you pay for it. So you should take advantage. Okay, the second disclaimer I have is, I'm going to, what I plan to do, and I can change my plan if you ask me for something else. Going over questions in this 1, 2, and 3 that I found particularly tricky, or not necessarily tricky, but particularly interesting in view of the things that you need to know for the final exam. However, I will not recycle these questions in the final exam. So these questions are gone. You'll never see them again. But of course, you will ask me questions on the same topics and on the same concepts. So the discussion here is with my knowledge of the final exam, okay, and the things that, sort of topics that you should be well versed on for the final exam. But you will be disappointed if you expect me to. It may happen that I do solve something that you do get exactly the final exam, but probability is close to 0. So I guarantee that we'll talk about things that will appear in the final exam, but not in the specific formula problem. Just that, so there is no recycling of products, but there is recycling of concepts. So this, I'll start with problems that appear in test 3, and then I'll go backwards. Okay? This is a problem that appeared in this last test, and you have a collision between a very small ball and a very large one. And you are told that the golf ball rebounds with essentially the same speed. Okay? This is what would happen if you had an elastic collision. Okay? If you have an elastic collision between two objects, one of which is very massive, then the massive one will move essentially, and then the small one bounces off with the same speed it came in. Okay? So you can see that, okay? You can think of the wall as a big object, okay? Throw a ball, okay, the ball bounces back at the same speed. Okay, this will be big. And there is a question about how the magnitude of the momenta of the objects are related after the collision. Okay, so let me see if I can switch here. I don't think I can project two things at the same time. I'll have to switch here. Okay, so we have these little ball, okay, going there with some velocity, V1 initial, and hitting this big ball that's not moving. And then we have this thing bouncing back, V1F, which is roughly equal to negative V1I. And we have this V1 here. And there is a question about what this one is doing. Okay? So, there's a question about momentum. Okay, the momentum is related to velocity. This way, it's the definition of momentum, mass times velocity, okay? So if I were to draw the momentum vector for the first ball, okay, how will I draw that arrow? Well, it is this arrow here, the velocity multiplied times the number m, which is a positive number. So it will be an arrow pointing in the same direction as the velocity, okay? The arrows exist in different spaces. The velocity arrow exists in the meter per second space. The momentum arrow exists in the kilogram meter per second. But the direction is the same. So this will be the momentum. Okay, and this one will have initially zero momentum. So P2 initial is equal to 0 because we know it's not moving. Okay? So if we look at the final, we are told that the little ball bounces back with about the same speed. Okay, so if I have to draw the momentum vector for that little ball, how do I draw it? Opposite direction, about the same length, okay, because mass times velocity, okay? So this will be like this. Okay, so this would be P2 final. Okay? Now, all the action here is along what direction? Okay, so I could take my x-axis just going here to the right, and in some particular units, I choose some units. I choose a new unit of mass or new unit for velocity so that the number I get is 1. Okay? So if I look at this in terms of components, here I have 1 for the little ball and 0 for the big ball. So if this one is 1 and this is 0, what is this one? This is -1. Okay? Now remember that momentum here is conserved. Okay? And so if I add these two, I get 1. If I add these two, I should get what? 1. So what should this be? 2. Okay? Make sense? Oops, sorry. So I can go very bit. Zoom. Yeah. Okay, so the thing is that this momentum, the momentum of this object, should be twice the momentum, the initial momentum of the small ball. Okay? So, and this is why, I'll come back to this. The correct answer here is the momentum of 2 final equal 2 times the momentum of 1 initial. Okay, so that's the correct answer. Now you may say, well, this is sort of strange because the big ball has twice the momentum of the little ball that was coming in, but if you do the experiment, okay, the little ball will bounce back and the big one will essentially not move. How come it can have twice the momentum? Well, because momentum is mass times velocity. So the mass of this ball is huge. So its velocity will be very small. M times V is 2 times the initial momentum of that, but V is going to be very small. If you calculate it, you see that it's inversely proportional to the mass. So if the mass is 100 times bigger, then the velocity of the big ball will be 100 times smaller or something like that. Okay? So it does agree with the intuitive notion that the big one should do much, and the blue one is the one doing most of the action. But if you look at the momentum, the big one is carrying twice the momentum of the little one. Any question about this?